Hello there, everybody. Toby Delbrick here. I'm going to show you how we can play with the noise tester filter to characterize and understand different denoising for DVS. I have jAER open here. I've assumed that you've installed the latest cut of jAER. And I'm just going to now show you how, if you run jAER, how to turn on this noise tester filter and enable different noise filtering. So let's assume that you have jAER and you've downloaded or somehow gotten to your computer the dataset papers, and it'll take this V2E test white dot clean, which is the moving dot dataset. You can see it consists of the moving dot here. Now I'll open the filter window, which shows you the chain of filtering that jAER would execute if you enable the individual filters. For example, rotation, region of interest, and different noise filters like background filter, order end filter, and so on. But the one we're interested in here is noise tester filter. If you don't have that, you can select the filters here. You may have to refresh the list, and then you can pick noise tester filter using camel case, NTF, like this. You see noise tester filter, it tells you what it is here, which is test background BA denoising filters by injecting known noise and measuring how much signal and noise is filtered. Now you can add that to the list. Actually, we have it already, it warns you, so we don't need to add it. You can see it right here. So let's cancel this. We can get rid of some of these other filters just to save screen area. I'll just do that right here. We don't need speedometer. Okay, so let's look at this noise tester filter. Well, here is the list. Now, if we expose the noise tester filter, it's a complicated looking beast at first. You can see here the different potential noise filters like background activity filter, spatial temporal correlation filter, double window filter, order end background activity filter, and one that's not in our paper, median DT filter. But basically you select the one you want using this pull down here. Right now I'll select none. I'll enable the noise tester. I'll turn off the overlay negatives for now. And now I see that added to the original signal is a bunch of background activity noise. If I accumulate the events with P, you can see there's quite a high rate of this background activity. And this is controlled now for synthetic noise by the leak noise rate and the shot noise rate down here. If I can now decrease the rate of shot noise or increase it. For the purpose of this demo, I'll just set it to 5 hertz per pixel. And now we want to see how well one of the noise filters actually works. So I can take the background activity filter, select it here, and you can see it's not filtering out hardly any noise, right? It's letting through all the signal, because you see here, if I zoom out with control mouse wheel, you see this yellow dot here shows the true positive rate. It's the rate of signal events from the moving dot that go through from 0 to 1. And this is the false positive rate, is the fraction of noise events that are going through. With the long correlation time of the BAF, the background activity filter, of 30 milliseconds for correlation, at this high noise rate, a lot of noise is going to go through. We can reduce that by reducing the correlation time, and now we see less and less noise goes through. At a certain point, you start letting through less and less signal as well. If I really reduce it down to like 1 millisecond, I filter out a lot of the noise. They say like 95% of it. You can see here that the true negative rate is about 97%. So I've filtered out all but 3% of the noise, but now the true positive rate is only 50%. I'm only letting through 50% of the signal. So in this way, you can interactively trace out the ROC curve by just sliding around the correlation time and see how this yellow dot moves around. If you want to see the history of those dots, you can set a ROC history length here of a few hundred samples, say 200. I can also use the mouse wheel for this. And now it shows you on here the legend. This is the time constant, tau, of the filter. If I now reset the filter, it should clear the ROC history. That's a bug right now, but I'll fix that. And now if I change the time constant, I can now see what happens. This is making correlation time longer, making it shorter. And now in this way, you can interactively gather this kind of ROC curve for a particular segment of the recording. If I want to just restrict myself to one segment of the recording like this, I can set an in and out mark with the square bracket keys. You see the left square bracket and the right square bracket. And then that restricts to a restricted part of the recording. And now over this restricted part of the recording, I can just slowly sweep the correlation time and get an interactive visualization of the ROC curve. Now let's compare that with some of the other filters. Instead of background activity filter, I can pick, for example, the order n background activity filter. Okay, now it does that. Now it's hardly sensitive to the correlation time at all. If I make it really, really long, this is a weakness of the order n filter. It has difficulty letting all the signal through, but it never lets much noise through. If I make the correlation time very, very short, eventually, when I go down below a millisecond or so, I start to let through, block more and more of the noise. But you have to make the correlation time incredibly short for that. If I pick, for example, here the double window filter, you can see it doesn't use a correlation time. It uses different distance and window length. And now to see that parameters of this double window filter, I expose the controls for it here. And now I can look at denoising control. So here's the window length, and here is the distance threshold. If I make the distance threshold bigger, it lets through more noise. It doesn't change the signal hardly at all. But now you can see the characteristic of this double window filter, that there's a zone of attraction. You see there's a cluster of events right around the signal event. If I slow it down especially, you can see there's kind of a cluster of these noise events right around the dot that is being let through. But that's the characteristics of this double window of the double window filter. Now compare that with the spatial-temporal correlation filter. Now the correlation time is only 2 milliseconds. The cool thing about the spatial-temporal correlation filter, in this case, with the number that must be correlated, the K, being set to 3, I can see that I'm able to set the correlation time up to quite a high value, say 15 milliseconds. You can see the number here. And I get almost to the perfect ideal ROC point, which is right up in the corner here. It's letting through all the signal and hardly any of the noise. And so now you can also play with other data sets. For example, the driving data set, much more difficult problem to filter this. Now you can see the ROC curve when I play around with this STCF and make the correlation time longer. Eventually I start letting through more of the noise. I'll restrict it to a part of the recording here, like this to this. And now if I play around, I can get the ROC curve. Let me slow down the frame rate a bit here. And I can trace out the curve here. And now I can compare this ROC curve just heuristically, right? This is not how you collect data for a paper, but just to understand the filtering and the effective parameters. So you can just trace out the ROC curve. And now you can switch to a different filter like BAF and trace out the ROC curve with it. You can see that the correlation time has to be a lot shorter with BAF. And you could see, I don't know if you noticed it, but the ROC curve is definitely not covering as much volume of the area under the curve. So I hope this is helpful to help understand how to play around with different noise filtering with the different data sets that we supply, the driving data set, the moving dot, and this nice experimentally recorded surveillance scene from the Capocaccia Neuromorphic Workshop Hotel, where there's just some people walking around. It's almost noise-free data. There is some background activity noise, which is caused by the APS frames being triggered. As I said, we also supply samples of raw noise recorded from the DVS under high light and low light conditions. And that looks like this data here. So if I open the AEDAT folder of our data set, we can go to measured noise. In there are two raw data sets, right? It's light background and dark. If you go to light background, this is an example of noise that you get under bright lighting conditions. And you can see here, if you accumulate the events, it takes a while for any particular pixel to accumulate one of these leak noise events. If you want to look at the statistics of this leak noise, CellStats Prober is a filter that shows you a histogram, either a frequency or an interspike interval histogram of the event rates. It's a complicated thing. Again, you have to set it up properly. You notice that it's frequency histogram enabled. We are treating each pixel independently, so independent pixels We've already set the scale here from a minimum interspike interval of 100 microseconds to a maximum of 100 million microseconds, so up to a 100-second interval between spikes events, and we're looking at the average ISI histogram here. And now if you hold it down here, you see that this is on a log scale because it should be log ISI enabled and log probability enabled. If we enable log probability, it puts a vertical axis histogram frequency probability on a log scale. Otherwise, it puts it on a linear scale. You can see here that under these light conditions, if I just accumulate these events, and of course it takes the ones that are spiking at a low rate a long time to accumulate, but you see that the average, there's a peak here around 3 hertz or so, as another one around 60 hertz. That could have been from flicker. And if I now look at it instead of frequency histogram, I look at an interspike interval histogram, we can see that the most frequent interspike interval in this data set is around, it's hard to say, around 300 milliseconds or so. Data recorded under low light conditions in measured noise. This is measured dark BA activity. You can right away see in the preview that the event rate is much higher. And it consists not just of on events, but also off events, because you can see white and dark events about equally distributed between the different types of events. If we use the CellStats prober to look at statistics of this data, you can see that now the interspike interval is much higher rate. It's around 100 milliseconds or so. If you look at the frequency spectrum, you can see the average event rate is around 10 hertz per pixel. So this real recorded noise can be used in the NoiseTesterFilter as an input. So if I go back to the NoiseTesterFilter and pick one of the recordings, where's that? So here's the moving dot. And now I can open the NoiseTesterFilter and open noise source recording. Now we can choose this noise source recording, dark BA activity.ae.dat. That now selects this as an input noise source. If we enable this filter now when we change the noise rate down here, it doesn't affect anything. This is real recorded noise mixed together with our clean model DVS signal. We can now study the effect, for example, of spatial temporal correlation filter on this, and we can measure the ROC curve for the STCF using this real recorded noise. Again, you can see it gets almost to the ideal point where almost all this real recorded very high shot noise rate, which you can see here, is removed by the spatial temporal correlation filter, and much less so by the most popular previous filters, the background activity filter. So we hope that's helpful also for your developments of future noise filters. And good luck with your developments.